Hi, this is Mrs. LaBarbara. This is Physics Chapter 9, Current Electricity Video 5. Today's topic is electrical energy. The objectives are: know that kilowatt hour is a unit for energy, know the quantities and its corresponding symbols and units, understand how current, voltage, and resistance affect energy, understand that energy can change forms, but it is always conserved, be able to determine electrical energy. Electrical energy. First, let's take a look at the equation. Energy or work equals power times time. Since there are three equations for power in this unit, so there are three equations for energy. VIT, I squared times R times T, and V squared divided by R times T. So which equation you're supposed to choose depends on what is given. The SI unit for energy is a joule. So joule, remember when we define work or energy, is force times distance. Force is newtons, distance is meter. Newton, again, is force. Unit for force, Newton equals to M times A. So Newton's unit is mass. The unit for mass is kilograms. The unit for A is meters per second squared. The whole thing times meters. So in the fundamental units, the joule is kilograms times meter squared divided by second squared. This is the expression for fundamental units for energy. A kilowatt hour is a unit for energy because kilowatt is a unit for power and hour is a unit for time. So power times time is a unit for energy. As a matter of fact, that is how electrical utility companies charges all the household by how much energy you have used. Now, how many joules is in 1 kilowatt hour? So we know 1 joule equals to 1 watt times 1 second. So we have to see how many kilowatt hour is how many watts second. 1 kilowatt hour equals to kilowatt is 1,000 watts. 1 hour is 3,600 seconds. So 1,000 times 3,600 is 3.6 times 10 to the 6 joules. So that's 3.6 million joules. Check your understanding. First example. Your 60-watt light bulb is plugged into 110-volt household outlet and left on for 10 hours. The utility company charges you 20 cents per kilowatt hour. What is the cost? So to find the cost, we have to see how many kilowatt hours is burning 60-watt light bulb for 10 hours. So E equals P times T. P is 60 watts times 10 hours. To convert this into kilowatt hour, we have to convert watts to kilowatts. So 60 watts is 0.06 kilowatts. One way to convert it is to use 60 times 10 to the negative 3. Remember, to convert is to divide by K. K is 10 to the 3, so 60 divided by 1,000, which gives you 0.060 kilowatt. And that gives you 0.6 kilowatt hour. And we know the utility company charges 1 kilowatt hour is 20 cents. So the cost is 20 cents per kilowatt hour times 0.6 kilowatt hour. That gives you $0.12 or 12 cents. Another example, a current of 40 ampere is measured in a 150 ohm resistor. How much energy is expended by the resistor in 20 seconds? So you know I, you know R, you know T. Look at the equation. I squared times R times T gives you 480 joules. Next one, an electric dryer consumes 6 million joules of energy when operating at 220 volts for 30 minutes. So in this case, give you E, give you V, give you T. How much current? What is I? So look at your equation, see what equation you can use. E equals VIT. To find I equals E divided by V times T. Now the only problem is in all these equations, T has to be in seconds. So you have to convert 30 minutes into seconds. You use 30 minutes times 1 minute is 60 seconds. So 30 times 60, you'll have 15.2 amperes. Okay, now energy can be transformed. This is energy conservation law. So energy is always conserved. Energy can be transformed, but is always conserved. The purpose of every circuit is to supply the energy to operate various electrical devices. These devices are constructed to convert energy of flowing charge into other forms of energy, such as light, thermal, sound, mechanical, and so forth. Use the complete sentences to describe the energy conversion that occurs in the following devices. Number one, windshield wiper on a car. So what kind of energy transformation is here? Well, windshield wiper is to convert electrical energy into mechanical energy. Next one, how about the defrosting circuit on a car? For defrosting circuit on a car, you convert electrical energy into thermal energy. Last one, hair dryer. Hair dryer in this case is electrical energy is transformed into thermal, so you have heat, into mechanical, kind of like your hair is blowing, right? Is moving, and also sound energy. So many forms of energy. Let's take a look at another example. Regardless of the method used to generate electrical energy, the amount of energy provided by the source is always greater than the amount of energy produced. Explain why there is a difference between the amount of energy provided by the source and the amount of electrical energy produced. Why is that? This is because all the equipment has friction, so energy is needed to overcome friction. Or energy is converted into thermal energy in the moving parts. That's again, really, you say the same thing differently. And all the devices also have sound energy, like electric hair dryer, even your vacuum have sound. Even the fan has sound. So all the energy converted into, like some of energy is converted into sound, but mostly is because of friction. Rechargeable batteries. So we use our phone. We have to charge our phone, right? Every night, or some other devices, you charge it. Rechargeable batteries really has nothing to do with charges. The name kind of deceiving. It sounds like you're running out of charge. It has nothing to do with charge. Rechargeable batteries relies upon a reversible reaction, right? Turning chemical product back into chemical reactant within the cell. That's what happens. So you essentially using electrical energy to convert the chemical product back into reactant. Then that reactant can do work on the charge. Then you'll have to have this cycle goes back again. Now let's check some statements, see if they are true or false. Are the following statement true or false? One electrochemical cell no longer works. It is out of charge and must be recharged before it can be used again. Remember, this is exactly the same thing we're talking about. When it's not working, has nothing to do with charge. Charge is there already because charges are part of your atom, your matter. Your matter is always there. It just cannot move anymore. It cannot move because it doesn't have energy. There is no energy to make it move. So the first one is false because it's never out of charge. Number two, an electrochemical cell can be a source of charge in a circuit. No, the source of charge is in the atoms. It's not in the cell. Cell provide energy source to move the charge. So number two is false. Number three, charge become used up as it flows through the circuit. Charge can never be used up. Energy is used up. So number three is false. Number four, charge flows through circuits at a very high speed. No, this is false. We talked about drifting speed is actually very, very slow. Even current can be high. That means lots of charges are flowing at once. Charge is moving at a very low speed. This explains why light bulb turns on immediately after the wall switch is flipped. Now, that's not why the the light turns on immediately. It's because charge is there. When you turn the switch, you give it a command. You provide energy, says time to march. So all the charge start to go. Number 5, local electric utility companies supply millions and millions of electrons to our home every day. That is false because what they supply is energy. They supply the energy to move the electrons already in our home, already in the wires, so they can do work. So all these statements are false. So quantities, symbols, and equations, units. The tendency to give attention to units is an essential trait of any good physics student. So many of the difficulties associated with solving problems may be traced back to the failure to give attention to units. As more and more electrical quantities and their respective metric units are introduced, it will become increasingly important to organize the information in your head. So this is the information kind of organized for you. It lists the quantities we have learned in this unit. You have volts, current, power, resistance, and energy. And it gives you the corresponding equations. It's your job to know what each symbol represents, to remember that, and the corresponding units. For example, all these are the unit for power: joules per second, watts, right? Volt times ampere, volt divided by ohm squared, or ampere squared times ohms. Here are the units for current: coulombs over second, or volts divided by ohms. And here is the unit for volt, is joules divided by coulombs. Ohms is volt divided by amperes. Here's the unit for joules. Electron volts, remember, that's a unit for energy. We also talked about kilowatt hour is a unit for energy. A watt times a second is a unit for energy, but watt times second is equivalent to joules. Volt times coulombs is equivalent for joules. This electron volts is not equivalent for joules. This is the other units, okay? As a matter of fact, one electron volts is 1.6 times 10 to the negative 19 joules. That's it for today. Thanks for watching. See you next time.